Yeah, welcome to May episode for Introduction to Astronomy, for another fun-filled where all the action is. So let's start with a story. I always like to start with stories, and it's called the twins paradox. So you get these twin guys, Roger and Trevor. They're 25, twins. And Roger decides he's going to get a little bit restless. So he's going to hop on a spacecraft, new technology, and fly off to Barnard's star system, which is about 7 light years away from Earth. And so he heads on over there, and then he realises, this is not all it's meant to be. Grass, it's one of those cases where grass is always greener on the other side of the fence, but as you get older, you realise it's brown on both sides. So he, sorry, that's a bit cynical. It's just a joke. So anyway, he decides to come back, but on his return, he comes back to Earth, and he finds that Roger's only aged 30, he's only aged 5 years, but his twin brother is now 73. How did that happen? So that's a lovely story, which we'll delve into that later in the talk. But who can tell me who was the scientist and who was and that was the name of the theory behind that makes all that possible? How we understand that? Yeah, it's Einstein's, and that's why tonight we're going to be talking about Einstein's theory of special relativity. And tonight we're going to lift the hood up and have a look underneath it and demystify it and really make it is pretty straightforward. It's just some fun implications. So let's start off with, let's give you 3 sticky messages. I'm going to give you them at the end of the talk, but I like to throw them up front as well. So you're going to learn 3 points to take home and tell your family tonight, if they'll allow you in the house. So the speed of light is the same for all observers in uniform motion. In other words, anyone travelling in a nice, steady, straight line at a normal pace without increasing or decreasing their speed, constant speed, the speed of light is always observed to be the same. Space and time that we imagine to be different, like we're in the star dome right now, that's sort of our space, but time, we're moving ahead as I keep blabbering on, time shifting forward, but you're going to learn that space and time are irreversibly entangled into one entity called space-time. And the third sticky message you're going to take home is that the implications of that last statement include differing observer perceptions of space and time. So it's not fixed. Space and time is not fixed. It's variable, and it all depends on your perspective as the observer. So let's have a roadmap of what we're going to do. So chapter 1 will be on the introduction. We'll talk about the definition of special relativity, what it's actually about. We'll talk a little bit about the background, what led up to Einstein to say, he didn't wake up one day, oh, I've got this idea. He developed this idea and had some thoughts. So what was the background that led to it? And then we'll have some fun talking about the implications of special relativity. And then I'm going to throw you your 3 sticky messages again. So, yeah, definition in the background. Well, this guy obviously needs no introduction. This is Albert Einstein. This picture was taken about 1905. It was his miracle year when he brought out 4 groundbreaking papers. One of them was special relativity, another one was a spin-off from that with E equals mc squared, very famous equation, equating mass and energy together, and of course the photoelectric effect and so on. So this is about the era when he came up with this, and what it means is that special relativity theory, it regards the relationship, it brings space and time together. It's the formula to link the two together into that one entity. And the special part of it, people say, why is it the special relativity? 10 years later, he worked on the general theory of relativity, which involves any sort of movement with acceleration. He uses the word special because it's referring to a special setting of just uniform, in other words, constant motion. It says here, the special setting of universal. Another word you'll see is, we often use inertial. So uniform, inertial, all means constant motion, no acceleration. You're not speeding up, you're not slowing down, you're not changing a corner at all. So it's that special setting of constant motion. You start bringing space and time together. So a bit of background, what led up to it. Of course, there's 3 giants, and arguably the greatest people scientists ever to have walked the planet, with Galileo, Newton, and of course Einstein. So let's start with these 2. And Galileo first came up, well, first of all, these two guys, all their research was done really on motion, observations of motion. And Galileo was the first, he created his law of inertia, which he put forward, which says the natural state of motion of an object is a straight line at a constant speed. In other words, if there's no friction, everything just travels in a straight line. If you want to slow something down, you've got to introduce a force. If you want to speed something up, you've got to introduce a force. If you want to change direction of something, you've got to introduce a force. The natural tendency of everything is just to keep going. Well, you might say, well, how come you boot a football across the room and it comes to a bit of a halt? Friction is the force there, the external force going on. But it's in classical example, space. You see an astronaut, he just gets a pen, throws it across the room inside the space station, and it just keeps flying like that. And you've got to apply a force to slow it down or alter it in some way. So that was Galileo's law of inertia. And then Newton came along. Incidentally, Newton here was, as you'll see, was born on the same date of birth. He was born on the same year that Galileo died, so he picked up the baton, so to speak. And he expanded on these laws of motion to create the principle of Galilean relativity. So already these scientists were thinking about relativity. What do different observers see and how are they related? And so Newton's principle of Galilean relativity states the laws of mechanical physics are the same for all observers in uniform motion, i.e. there's no preferred or special state of uniform velocity which includes at rest. So what all that means is that this guy kicking a soccer ball in the middle of the park, just booting it around or throwing a ball up in the air or whatever, it doesn't matter whether he does it in the park or whether he does it in a plane travelling at 600 kilometres per second. You throw a ball up in the air or you boot it, it behaves exactly the same. You don't on an aeroplane or a train suddenly have a happy moment and jump for joy and end up flat on the back of the plane on the train, do you? On the back wall. You'd only be happy once. So the laws of physics, and we take that for granted, don't we? You might be on a plane trip and you want to throw a ball or something or a bit of paper at someone, 2 or 3 rows ahead. Hey, like that or whatever. You don't expect it to fly back at 600 kilometres back, per hour to the back wall. We just take it for granted, but that is a law of physics. And that's really, really important. So the laws of mechanical physics are the same for all observers in uniform motion. So if you did a scientific experiment in the park, or you did it in the lab, or you did it in an aeroplane, you get exactly the same results. So, and that includes at rest. So I'm moving at a constant speed, or I'm at rest, the identical laws of motions. So, and another thing I put here, so just a little bit of food for thought. So for example, here's a classic one. You're playing table tennis, and you decide to hop up on the plane. And you have a game of table tennis, and you're hitting the ball backwards and forwards in this your AA80. What would you expect to happen? Just normal, wouldn't you? The ball go backwards and forwards. You're not having to compensate the fact that you're up in an aeroplane. How about if you had your cup of tea sitting there and you wanted to heat it up and put it in the microwave? So you know all these laws here, and you say, yeah, I take that for granted. But here's something that wasn't around in Einstein's day, but we take it for granted. What would you expect to happen if you're in a microwave on that plane, and you put your cold cup of tea, and you wanted to heat up and push the start button for a minute or two on high? Is it going to stay cold? Are the light waves going to go from cooler, get stretched out because you're travelling at 600 kilometres per hour and get stretched out into radio waves? In fact, your tea never gets warm. Because you're travelling at that pace, are the wavelengths of light going to get crunched up and it's going to heat up a lot quicker because high energy photons? No. It's exactly the same, isn't it? And already you're probably getting where I'm heading with this, where Einstein was heading with it all. What makes light different to anything else? When he first created it, we thought, no, that can't be so. Stop and think about it. In your microwave oven on an aeroplane is just a classic example. So let's start talking about relativity. So we're going to start first of all with this, the Galilean relativity principle. So how does someone else observe and record events from a different inertial frame? In other words, a different reference of motion. And here's a classical one. Let's look at this example here. So you've got this guy sitting on the back of a truck, and he's throwing a ball up and down, and that's how he sees and how he records that motion. And here's your coordinates that he would use. X, Y, Z for your coordinates and T for time. But supposing you were sitting on the side of the road and you saw this truck drive by, you're not going to see what this guy here is experiencing, or someone else sitting on the truck. You're going to see that ball arch over in an arch and come down like that. Once again, you take it for granted, but that's what's happening. You just don't even think it's second nature to you. So if you're trying to describe that with a set of coordinates, you call what we call a transformation, and this is called the Galilean transformation. And notice the only thing that's changing here, time is not changing, its distance is changing to allow for the velocity or the speed of that truck. That's the only thing you really have to do to change the set of coordinates from what this guy is seeing to the set of coordinates to describe what this guy is seeing. All you're doing is changing the horizontal axis to incorporating the velocity of the truck, and that will just beautifully with time describe a nice arch there. But already I'm trying to introduce the principle that the same activity is going on, a very simple activity, but you get two different observers seeing totally two different things. And you might say, big deal, but most of us, we take that for granted, but we don't actually, doesn't sink home what's actually going on. That's a very important law of physics. So that was all fine, and life was good when they thought, yeah, we've got the Galilean transformation, that makes sense. That's classical physics. I think we can safely leave science there. And then along came this Scottish genius physicist in the 1800s. Who can tell me who this guy is? Maxwell, yeah. Thanks, George. Yeah, Maxwell. So this is James Clerk Maxwell, and brilliant man. You know, when you talk about who are the greatest scientists ever to walk the planet, some people will bring up this guy. Very, very clever guy. Sadly, he died when he was about about 50 or so, very sadly. But so Maxwell discovered that light was in actual fact propagation of electromagnetic waves. It was something. He described what it was. So let's delve a little bit deeper into that. And what we mean by that is you get an electrical current or electrical field that's propagating through space. And as that changes, it generates a magnetic field. And as the magnetic field generates electric field, and it's just a series of propagation. So you get electric field, it propagates, then that moves on to a magnetic field. The magnetic field creates electrical field, and so on and so on. And he worked out this, he called it electromagnetic radiation because it was a propagation of self-propelling sort of electric and magnetic fields, all getting laid down, heading in a direction. And at the time they decided, oh, I wonder what electromagnetic radiation is. And at a similar time, someone actually worked out what the speed of light is. Maxwell, with his equations, which I'll come to next slide, he had already calculated what the velocity, how fast these electromagnetic radiation propagating waves should be travelling through the vacuum of space. And lo and behold, when someone measured the speed of light, it was exactly the same, and they realised that's what made them realise that that's what light is. It's the propagation of electric and magnetic fields in a wave-like fashion. So he described it in these four straightforward, simple sort of equations he put forward. And these four equations describe everything we know about electromagnetism. Very, very important. So in these equations, there's two constants of nature that he discovered, which are measurable. And the first one is epsilon, which is in the equation here, and mu. So both of these are constants of nature which can be measured. And what do they stand for? Epsilon refers to the permittivity, or in other words, the resistance of free space to formation of electric field. Mu refers to the permeability, or the resistance of free space to allow magnetic field lines to run. You might say, oh, big deal, yeah, okay, I think I get that. What is the significance of those two statements? That's telling you the nature of this universe, its vacuum space that's out there, and the resistance of space to laying down massless electromagnetism. Electric field's getting laid down. There's a certain resistance. It just doesn't happen instantly. A magnetic field's got to then get laid down. It doesn't happen just instantly. There's a bit of resistance going on in the vacuum, and that's a natural state characteristic of our universe. Now, the universe might be a little bit different, but for our universe, for what we know, that these are constants of nature, and this is the natural resistance. In other words, it slows stuff down. Nothing happens instantly. So from these formulas, you can actually work out here, because it's got c, and that's the speed at which the velocity at which these electromagnetic propagations should take place. And you rearrange these formulas, and what do you get? C, the speed of light, it's the inverse of the square root of mu and epsilon. These are constants, in other words, characteristics of natural ones of our universe. You can measure these, and lo and behold, you can actually work out what the speed of light is. People often say, why is there a speed of light? Why doesn't light just zip through? It's got a resistance. Vacuum is something, and I think as you learn in particle physics and stuff too, a vacuum is a very, very busy place. It's teething with activity, particles coming in and out of existence. It's a foam of activity. And it's going to have some resistance, like water's resistance, air's resistance to light. The universe, the vacuum of empty space, has resistance to light. And it's through these constants here that he brilliantly put all these together, worked out with C. And so from here it works out to about 3 times 10 to the 8 metres per second is the observed speed of light. What's special about it? C is a universal constant. People get hung up about the whole concept of speed of light. It turns out that C is a very common constant that comes up time and time again in equations, physics equations. I think one of my last slides will talk about what is the significance, or what's special about light. And the answer, as you'll find out, is nothing. There's nothing special about the speed of light. It just happens to be the nature of our universe. So that was Maxwell did that sort of work. And then who can tell me who these two famous sort of experimental physicists are? And they performed a very important experiment in 1887. Michelson and Morley, yep. Very, very clever, renowned, known for their high precision experiments. And what they did, I think it's my next slide. Yeah. So with this thing, so they worked out, okay, they suddenly understood light is a propagation of these alternating electric and magnetic field lines going through. So they propagate in waves. Waves need something to propagate through. Waves in the ocean, sound waves, waves through the air and stuff. You need a medium, some sort of substance for waves to propagate. That was pretty straightforward in the 1800s. It makes a lot of sense. So they hypothesized that maybe the universe was permeated with very tenuous ether, some sort of substance that was just flowing or just suspended in the universe, and everything as the sun traveled around the galaxy, it went through this ether. And when the Earth orbited around the sun, it too just worked its way through the ether. So a few people thought about it, including Michelson and Morley, and they thought, well, if this is so, there are going to be certain times in a year we're going to be going perpendicular or with the ether as the sun and the Earth moves through this way. We're going to be going with the ether, and light's going to be travelling with us. So the speed of light might be a bit quicker, or appear quicker. Say if we're going back this way and we're going against it, it might be maybe the light's going against the ether, or we're going against the ether. Maybe the speed of light might be a little bit different. So they set up an experiment which was very accurate, total confidence in it at the time, and still to this day, very highly sensitive instrument that could tell them pretty much they had it down. You might say speed of light, measuring in the 1800s, absolutely, they could measure it. So these two guys, they thought they would create this instrument that could measure the speed of light and measure it at different times of the year. And so the instrument would be picking light up at different orientations, if you will, to this ether that the Earth and the sun was quietly working its way through. So that in theory they should pick up a difference in the speed of light. But lo and behold, they found there was no difference. Whether it was April and they were pointing that way towards the ether, or October pointing that way against the ether, whether they were going perpendicular to this hypothesized ether, there was no difference in the speed of light. So that caused a bit of a stir and got a lot of people thinking about that. One of the times it sort of put a big downer on the whole idea of the ether, and well, maybe these particular light waves don't need a thing to go through, because if there was an ether there, we would have picked it up. So that put a big doubt on that, but also it got Einstein and a few others thinking, well, maybe there is no ether. Maybe there's more to the story about light than we think. And then these two guys, characters, so Lorentz and Fitzgerald. they stated that the speed of light does differ. There's an ether out there, the speed of light does differ. We just have not measured it that way. Our instruments have showed that the speed of light is the same. Why? Because they had this ad hoc hypothesis, don't know where they got it from, some packet of Cordies, who knows, but they got some sort of hypothesis they picked out. They said there was no, and it was just ad hoc, that the length of objects as they travel through the ether in motion, they contract and shrink down a little bit. And that's the reason why we show this apparent observation that the speed of light is exactly the same. So that led to an equation. They actually sat down and worked it out. If that was so, if our hypothesis is right, let's work out how much shorter this thing would have to be, the length would have to contract to make this so. And they came up with this equation here, the Lorentz-Fitzgerald transformation for length contraction. It describes how much an object contracts for a given speed. So here is, you've got the length of the object as you observe it after when it is travelling through the Earth, and actually what your instrument's actually recording with. This is what they call the resting length. In other words, if you had the instruments and they weren't travelling anywhere, just sitting in a nice stationary state when you first measured them up before you set them up, that's the resting length. And there it is, it's over the square root of 1 minus, the v represents the velocity at which an object or the instruments are travelling through space, and c, the speed of light. You might say, whoo, how did they get to that? You're going to see that in a minute, I suppose. So they came up with this formula, they just came up with this ad hoc hypothesis that things shortened, and that was why the speed of light looked the same. But speed of light did differ, and they worked out how much. So interesting enough, the formula works, as I'm about to show you, but for the wrong reasons. So yeah, then along came Mr. Einstein, and three things actually. As a child, he'd always had thought experiments about light. He just had this real thing about light. And he often asked people, I wonder what it would be like if I shone a beam of light and could run or fly in an airplane. They probably didn't have them, it was more trains in that days. If I had a fast train, just hypothetically, if I could keep up with light, what would I see? If I outshone light and held up a mirror, would the mirror just look black? This is the sort of stuff that Einstein, when he was young and even a child, he was throwing around in his mind. And then he sort of got inspired by Maxwell's equations that the speed of light showed a constant speed. It was actually a physical property. There was nothing magical about light. And as I jumped ahead a little bit of time, I showed you the microwave situation in the aeroplane. We know now there's nothing special about light, but he was one of the first guys. He said, look at Maxwell's constant, look at those equations that tell us about the speed of light. That's a property of the universe. What's different to that, to the laws of other laws of motion and so on? But also it was that Michelson and Morley null result that said the speed of light, the instruments never detected any difference despite different orientations through the hypothesized ether. So that got him thinking and inspired. So he then went on to extend the Galilean relativity principle to include light. And that's where he came up here. His theory of special relativity was based on two postulates. One is, which we've already seen, the laws of physics are invariable and identical, they remain the same in all inertial frames of reference, meaning that no matter what, as long as it doesn't involve acceleration, but at a constant speed, doesn't matter if you're just still, whether you're moving this quick or whatever, the laws of physics are all the same, whether you boot a ball in the air and how it comes down or whatever. But here's the interesting one where he threw the cat amongst the pigeons, which went against everyone's intuition at the time. He said the speed of light in a vacuum is invariant, remains exactly the same for all observers, regardless of the motion of the light source or the observer. So what that means, if I was with a torch over here, and say, for example, Andrew stood over there and I shined a light at him, he had an instrument to measure how fast the light beam, and I shone my laser at him, he would come up and say, well, it was exactly this, 3 times 10 to the power of 8 meters per second. What would it be if I started running towards Andrew at half the speed of light, charging towards him, shining that light? What would his instrument show, according to Einstein? Exactly the same, yeah, 3 times, he'd say, it's exactly the same. How about if I ran backwards at half the speed of light and kept shining it to him? Your intuition tells you, oh, it must look a lot slow. What does it measure? Exactly the same, 3 times 10 to the 8. It's just counterintuitive to what we're brought up with. So it was Einstein, and this was all about. And he said there's this particular second principle. And he thought, what makes light anything different to anything else? The laws of physics should be the same. So another one, cool little story is Bob the Sprinter. So tell me the solution to this. So there's this guy called Bob, and he tries to run faster and faster and faster, and takes all these steroids and stuff. And then he gets caught and gets booted out of the running thing for a year or two, has to go and sit on the sides. So he uses that time to get really, really super fit. And he says, I'm going to come back and prove to the world. I'm going to run as fast, if not outrun, the speed of light, a light beam. I'm going to have a competition, set up a light beam in the stadium. We'll shoot it across and I'll run at the same time when the gun goes off. And I'm going to train so hard, I'll keep up with that beam of light. So the day comes, the stadium packs up, and the gun goes off, they shine a beam of light, and out Bob the Sprinter, just out of the blocks, and it just blows everyone in the stadium. Holy! He's travelling, this light beam travelled at 3 times 10 to the 8 metres per second. Bob travelled at 2.9 times 10 to 8 metres per second. He was keeping up with the light. He didn't quite get there, but he was keeping up with it. Pretty impressive. And everyone, wow, Bob is a hero. He's redeemed himself. Let's go and congratulate him. So someone went down into they found him underneath the stadium, just in the changing shower room area there. And he was there crying his eyes out. So they said, what are you crying for? You've done an amazing feat. Why was he crying? Why was he upset? Because as far as everyone else was concerned, the speed of light just zipped across and he was keeping up with it. But as far as Bob was concerned, the speed of light was continuing on. He was observing it to keep moving away from him at the speed of light. He was the observer. To all observers, the speed of light is the same, irrespective of the motion of the observer or the emitter. So as far as Bob could see, the light was always a certain distance ahead of him. He could never, ever, ever catch it because that was the speed of light. But to everyone else, God, he almost did it. So it was just a neat counterintuitive thing that's going on because of this Einstein statement. So, and it really has some really cool implications involving the entanglement of space and time, which we'll talk about. So that pretty much sort of covers what I rattled on about. You've got your observer here. This guy's travelling at 0.8, the speed of light. This guy at 0.9. With a beam of light here. This guy sees the light shining at him despite them heading towards each other. It's sort of their combined speed, which we think of intuitively. This person still sees that light at the speed of light, c. This guy here sees it exactly the same. So everyone observes the speed of light exactly the same regardless of the motion of the observer or the emitter. So let's move on to the implications of that statement. It involves time dilatation, length contraction. We'll talk more about that. Twins, Roger and his twin Trevor. And then we'll talk about things happening simultaneously. And then we'll talk about the universal speed limit. So, time dilatation. It's all about how time is perceived. And that's one of my first statements is right at the front. Space and time are one entity, and both are invariant. They're not set in concrete. Rather, they're both variant. They're not set in concrete. They can change. It all comes down to the observer's perception. And moving clocks appear to go slow. And I'm about to explain in this more depth, but this is just what time dilatation is about. So here's you've got a couple of twins here. Same time, clock's the same. Twin B heads on out, comes back. Twin B, it's only gone. The time has only gone that little part there. But twin B, it's travelled proportionately, so that's 2, 3, 4, 5 times as much. Twin B's clock ran slower because it was travelling relatively to twin A, and so hence aged less. So we're going to go through that. But that's what the concept of time dilatation is about, just like we spoke about Roger and Trevor. So let's move on to that. So you might think, whoa, and there's some big formulas coming up, and how does all this work? And it really is simpler than you think. So here it is. So time appears to go slow due to light travelling a further distance but at the same speed. Because what have we just been told? The speed of light is the same to all observers. So let's have a look at situation A. You've got this sort of clock, if you will, a light clock. And it's at rest, whereby a source of light sends a beam of light up here this distance, hits the mirror, comes back and hits the sensor. And that's sort of like a light clock, and it's sort of a set distance, and the speed of light is exactly the same. It goes up there and it comes down. Life is good. That's all pretty easy to get. How about this platform here? You put this experiment on a train platform or something like that, and you had it moving quickly along, and you sat on the train station platform. What would you see? So if you're on the train, you're going to see the light go up and down, up and down. But you on the observer on the platform, as this moves across at velocity v, the instrument's moving across at velocity v, you're going to see the light go up like that, hit the mirror here, and come down, a nice little triangle like that. And what velocity are you going to see that light travel at? C, the same velocity. But look, it's travelling a lot. You know, common sense intuition tells you, what's the distance between here and here versus here and here? Which is the longer distance, A or B? B, absolutely. It's a much longer distance. But what did we observe? The speed of light was exactly the same. Something has to change. And here it is here. So light is observed to travel further in B. And also we all agree upon that observed to travel at the same speed, that the light was observed to travel the same speed, A and B. The light doesn't care. It travels at the same speed to you, the observer. We all agree that speed, velocity, is distance over time, you know, like kilometres per hour, metres per second. Speed is about distance over time. So we all agree to that? Yep. Okay, so there's our formula again. So if the observed speed of light in A and B is exactly the same, so the speed remains constant, but the distance increases, to keep that figure the same, time that figure there must be bigger. Because say, for example, speed, say it's a factor of 2, and you had the figure sort of 4 over 2 here, so it was 2. Suddenly if you increase that to 3, and you increase that up to 6, that's going to be 3 too. You know, the ratio's got to increase. So if the speed is constant in all the situations, but you're increasing the distance, the time must increase. So what that tells you is that to an observer, this whole process, this sort of process of this happening must have taken a lot longer. The internal clock must have slowed down. But if you were sitting on that train, you'd see it go up and down like that. Now, you might say, well, so are you all happy with that? That sort of, it just makes sense. The time is longer, so that clock is ticking slower. And well, let's explain it a little bit better. So by how much do we calculate it? It comes down to simple geometry. Pythagoras' theorem that we learnt in sort of school, sort of early on in school. That if you get a right triangle like that, and say you put assign this side as A, this side is side B, this side is C, that the square of this side plus the square of that side equals the square of this side, A square plus B square, C square. Everyone's happy with that sort of Pythagoras theorem that we learnt in school? Pretty straightforward. You might think, what's that got to do with relativity? Here is your situation. So here, remember we said that, that the formula, that velocity is distance over time, which you just rearrange it. Distance equals velocity times time. So the platform moving across at velocity v, its distance must be velocity t, so you just divide it by 2 because we're only interested in one. We want to split it up into a nice triangle, so we're just splitting off half the distance. So that's the velocity at which that platform was travelling times the time recorded, divide by 2, and that's your distance. Likewise, the distance here is the speed of light times time, divide by 2, and your distance here, you know your distance because you know how high your clock is. But so look, with your formula, just like with your A square plus B square equals C square, you just substitute it in. So here's your A, so it's V2 divided by 2 squared. Here's your D, you throw that in squared, and that must equal the CT divided by 2 squared. We know what V is, because we did that. We know what D is. You rearrange the formula. We know what C is, 3 times 10 to the power of 8 metres per second. So from there, what's the thing you can solve? You can solve it for time. You know C, you know D, you know V. You rearrange the formula, you can work out the time that you perceived that to happen. The guy sitting on the train saw the clock go up and down like that. You saw it going like this. And there's a simple formula just using Pythagoras' theorem to make this formula here, and this is it. So you can see where they're getting it. I've got a little video that actually shows you briefly how you actually form that. So this is the time measured on the moving body. In other words, I've added these little bits in here. This is the observed or perceived time by someone sitting on the platform, that time there. T0 represents the time measured on the stationary body. In other words, the passenger, as far as the passenger is concerned on that train, he's still in his science experiment. This little light clock's working just fine, thank you very much. That's his time, that's his clock. And you put it over 1 minus the square of the velocity of the train at which it's moving, divided by the speed of light. And this here is known as the Lorentz transformation. Where have you seen that? It's very similar, isn't it, to Lorentz-Fitzgerald formula for the transformation. Because once again, they got the formula right, but for the wrong reasons. Because they did the math to match the observation, not the other way around. They found the formula that they wanted. And I think it's coming up short. Yeah, this is it here. So let's just see if I can operate this. It's just about a 2-minute video, just to talk about what we've talked about.
Slow down when they were in motion. The essence of his reasoning can be seen with the aid of the simplest possible clock. 2 mirrors a fixed distance apart, with a light beam bouncing back and forth between them. Each bounce of the beam is a tick or a tock of the timepiece. To Henry, his clock is stationary and altogether ordinary. But for Albert, that clock is moving. And between tick and tock, he sees the light beam trace a diagonal path, which means it's traveling a longer distance. But the speed of light is the same for all observers, so the light must take a longer time to travel the longer distance. Therefore, Albert believes the moving clock runs slow. But how slow?
The relativity of time is derived from the right triangle formed by the distances traveled. The Pythagorean theorem shows that the path of the moving light is longer than the distance between mirrors. By the factor 1 over the square root of 1 minus v squared over c squared. This factor occurs so often in relativity that it is given its own symbol, the Greek letter gamma.
So to an observer at rest, a moving light clock seems to be running too slowly, by the factor gamma. A ruler, or anything else in motion, also seems contracted by that same factor.
That video just sort of shows it. Yeah, the clocks do tick differently. And that formula, when you first look, you think, whoa, that's a big complicated formula. It was actually derived, very simple. And if you didn't have to follow, it was probably too much to follow at that one moment in time. But you could see it was just a matter of shuffling the figures around from Pythagorean theory. And there it was, that's how they got the formula. So that was time dilation. In other words, moving clocks appear to be going slower, not to the person who's moving, but to the observer. And so that was how the perception of time gets changed. How about the perception of space? Space gets changed too, or the perception of space with movement. And it's called length contraction. So moving objects and distances appear to shorten as you travel. Instead of clocks slowing down, they slow down, but also lengths appear to shorten. So space shortens essentially. How much? Where have you seen that formula? That's your length formula. So this L represents the observed length when you're seeing someone travel at high speed, a ruler traveling at high speed. That's how what you measure or you perceive the length of that ruler to be. The person who's hanging on to that ruler, traveling through space at almighty speeds, They will tell you, no, the rule is this long, it's resting length, and it's just the square root of 1 minus v squared over c squared. There's no need to be afraid or phased by that equation at all. It's just derived through the simple right-angled triangle formula of Pythagoras theorem. Now, just a comment here, the length contraction is in the direction of motion that things start to shrink and get shortened. So, yep, length contraction occurs in the line of direction. So that's the formula there. So you've seen that. That was from my previous slide. And like I said, they got the right formula, but for a different reason, the wrong reason. They looked at the results and sort of, how can we make a formula to match this? And they created the formula, of course, and Einstein went the other way around and worked out in theory what it should be, and the observations matched. So this is just as in your handout here, this is time dilatation. So you can see the faster you get to speed of light, the faster someone observes you to be travelling, your clocks get slower and slower and slower and slower until you're almost to the speed of light and your clock's coming to a complete halt. Length contraction, as you observe something to go faster and faster and faster, as you're approaching the speed of light, that length or that ruler gets shorter and shorter and shorter and shorter to the point, should it reach the speed of light, you've got no ruler left. So moving clocks appear to slow down, lengths appear to shorten by the factor of that equation, the Lorentz transformation. So that formula is very general. And as the documentary said, it's actually just labelled gamma. It's used so often in physics. So there's lots of things to confirm special relativity. Atomic clocks, they're very, very accurate. You have an atomic clock on the ground, you put an atomic clock in a jet flying at high velocity, the clocks will keep different times. The clock travelling in the jet, travelling at high velocity, will tick slower than the atomic clock on the ground. That's been well and truly proven. GPS satellites, they wouldn't work unless you have to factor in the fact that they're high velocities, they're travelling. You've got to factor in relativity for their timing. Your electronics, your TVs, your watches, your mobile phones and stuff, that's all electronics. That's all electrons and stuff zooming around at huge velocities. If they ignored the laws of special relativity in designing these watches and mobile phones and television sets, they wouldn't work. So what more evidence do you need when you go home and turn the TV on? And you go home to the family and say, I see you're checking out special relativity. But I think one of the more nature's really cool one here has got the muon paradox, which is really cool. Nature actually shows us that special relativity is so. So these things called, muon is a subatomic particle. It's the heavy cousin of the electron. It's very unstable. It's got a very, very short half-life, so it doesn't hang around for long. And it's high energy situations that they are created. So you've got cosmic rays, which are heading towards Earth and slamming into our atmosphere high up. And cosmic rays are high velocity, high energy charged particles. Where have they come from? Probably things like supernova explosions across the galaxy and stuff. They're out there and they slam into particles in the upper atmosphere. And for a brief moment in time, these little subatomic particles called muons are created high up in the atmosphere. These muons then travel, because there's been a lot of energy imparted to them by these charged particles, cosmic rays travelling close to the speed of light. And the muons get created up here and they head on down towards the ground at 98% the speed of light. They've got a mean lifetime about 2.2 microseconds. So their time to reach the ground is 15 times their mean lifetime, which immediately tells you the chances of finding them on the ground, according to Newtonian physics, is pretty slim, pretty negligible. You're not going to find many. Yet Newtonian physics predicts negligible amount of muons. There's just not enough, almost all of them are going to have decayed by the time they reach the ground. But you put your muon detector on the ground and you wait, and you start thinking, aha, I know that formula from Stardome. I know that formula, that's why my TV works. And what do they detect? There are good appreciable quantities of muons that they do detect because of special relativity, time dilatation, and length contraction. Now let's split that up. You say, well, what's going on here? So from our perspective, the observer, if we were, just hypothetically, thought experiment to observe that muon, we would see their clocks ticking a lot slower. So their half-life suddenly, to us, our perception on the ground, is a lot longer, so they're living longer, so they've got more opportunity to get to the ground. From the muon's perspective, as a thought experiment looked out, instead of looking down and seeing 20 kilometres to the ground, the muon in that velocity would look down and say, oh, it's only about a couple of kilometres to the ground, we've got plenty of time. And so it's for those two reasons that, yep, the muons, despite their natural half-life of being about 2.2 microseconds, they quite happily travel down 20-odd kilometres, which in theory should not happen. Why? Special relativity. They're travelling at very close to the speed of light. So that's nature's proof to us, that special relativity, but we don't need that for our, we don't need that proof. We've got plenty of our own, thanks very much, but that's a pretty cool paradox. Now let's get back to Roger and Trevor. So why the difference here? So remember, Roger hopped in his ship and travelled at 0.9 times the velocity of light to Barnard star, 7 light years away, turned around, came home again. They were both 25. Roger gets back. He's only aged 5 years and Trevor's 73. What was going on there? So let's have a look at it. From Roger's perspective on the spaceship, his clock was running normal time. He said, look, I'm standing here, I'm at rest. My clock's at rest to me. Everything's running normal time. But he looks out his window and he doesn't see Barnard star 7 light years out. He sees the distance because he's travelling at high velocity. So far as he's concerned, he's stationary, but he sees the rest of the universe around him is speeding. So he sees length contraction. So he looks out and it doesn't see 7 light years. He says, oh, it's only 2.2 light years to Barnard star. That's no problem. And of course, then he turns and comes back again for another 2.2 light years. So it's roughly 4.5, just rounded off to 5 years. But you can see the reason that he only aged approximately 5 years and came back age 30 was because he perceived the difference of length contraction. It was only about 2.2 light years. These figures are actually, that was one of our exam questions in cosmology. So the figures are actually pretty close there. So it's about 2.2 light years versus 7 light years each way. From Trevor sitting back on Earth, what's his perspective? He still sees the distance, 7 light years, but he sees Roger moving along close to the speed of light, and he sees Roger's clock running really, really slow. So in other words, Trevor feels like Roger's clock is running slowly, and Trevor just sits there and waits for another, sort of 50-odd years for Trevor to get back. But Roger, as far as he's concerned, it only took 5 years there and back. Roger, it took 24 Earth years each way. Now, you might say, and I remember first doing this as a thought experiment, first came across all this, and I thought, well, hang on a minute, what's wrong with this? Roger's travelling at this fast velocity, seeing this, but you could argue the same back, Trevor as well. So you could argue quite happily that they should remain the same, but there is a subtle difference here. Anyone know what it is that actually makes this happen? What's that? The acceleration. Acceleration, yeah, George is right. It's the acceleration. It's a situation of asymmetry. The fact that Roger had acceleration and deceleration going on in the process, and that's what teases all this stuff out to reality. It's sort of an asymmetrical situation. So Trevor was just continuing at a constant velocity, so he perceives all this to be happening, but Roger was asymmetrical. He evolved acceleration to get up that speed and deceleration. But those figures, that's what would happen. It's called the twins paradox. Pretty cool. So how about simultaneity? Simultaneity of events. Yeah, we all agree if something happens on the other side of the room or whatever, we all agree what happened and what order and so on. But suddenly we're starting to play around. We've just told you how it comes down to motion. Space looks different perspectives. According to your motion, time has different perspectives. So it follows from there that people agree and disagree on what occurred in what order. And the first simple example is, let's look at a train. So this is from the perspective of someone sitting on a train. Trains, it's zooming along here, and someone's on the train, they have a light beam, and the light beam heads in each direction. As the train travels, they're in the train, and as far as they're concerned, they're at rest with that light. So they see that light in each direction, the same velocity. So as far as they're concerned, is they would say both light beams shone at the same time from the middle, hit the front and the back of the train exactly the same time. That's what an observer on the train would say. It was simultaneous. If you were sitting on the platform and that train was zipping past at some high velocity, by the way, all these effects do happen at low velocities, we just don't notice them. but they are happening. You hop on a plane to fly to Melbourne or Sydney or somewhere, you actually are gaining a microsecond on someone else. You just don't notice it. Certainly not enough time to slip a cold beer down at the airport anyway. Though having there's a bar on the plane, you could probably still slip one down, I'm sure. But anyway, I digress. So he sees this guy sitting on the train with a light beam going either way, but he also sees, to him, the speed of light is the same. So what he sees is, of course, because the train's moving in this direction here, going that way, so he sees the beam of light's got a shorter distance, so it whams into the back wall and then whams into the front wall. So someone sitting on the platform of the train would say, no, I disagree, that light beam shot out. It actually hit the back wall before it hit the front wall. Or if they had a sensor on each wall, they'd say the bell went off here and then it went off here, as opposed to this guy here would say, no, the little sensors went off at the same time. So that's this very simple explanation of why the sequence of events differs according to your observation and motion. How about a train travelling at 4/5 the speed of light in this direction, going that way, from left to right? A lightning bolt hits this tree and this tree here at the same time as far as the observer is concerned. How about this guy here sitting on the train? Would he say the lightning hit both trees at the same time? Or would he say it hit A first and then B, or B first and A, or both at the same time? He's going to say it hit tree B first because of length contraction. He says the distance between here. Remember the velocity, he's travelling towards there, he's travelling towards that tree. The length contraction says that's going to be a very much shorter distance. And just the fact that he's travelling in that direction at that high velocity, but he sees the light travels at the same velocity. So if the lightning hit this tree, it's got a shorter distance to travel to him here, but it's got a longer distance to travel here. And as far as he's concerned, the light from that tree coming towards him is exactly the same velocity as that tree. So this observer here says, no, the lightning hit both trees at exactly the same time because the light travels at the same time, at the same pace, and the distance is the same. This guy here says, no, I see both beams of light from both trees travelling at the same velocity, but this was a lot shorter. So B was struck first. Similar situation here, the lightning. This person in the spaceship, he would say, look, it struck B first and then A. This person down here says, no, it hit the both at the same time. So I've got another little video here just to highlight that point.
Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion. However, as
a nice little illustration. It was a sort of nice visualization. sort of how simultaneity is another whole implication of it all. So have at the universal speed of c, why can't an object travel faster than the speed of light? That all comes down to, there's another thing we haven't mentioned yet, is a concept called mass. And there's two explanations behind it, but it's all to do with relativity, relative mass. And the intuitive sort of explanation is that mass is observed. So here's your resting mass. If someone was travelling at a high speed, and first of all I should say, what is mass? Mass doesn't necessarily mean how big you are or anything like that. The definition of mass is the resistance of an object to be accelerated. It's inertia. So if something creates a lot of force to push it along, that's of a higher mass than something that's easy just to give a poke and it goes along. So that's the definition of mass. And so as your velocity gets higher and higher and close to the speed of light, your perceived from an observer, your mass goes up and up and up according to this Lorentz transformation formula. So as the mass increases to infinite levels, you can see here's the velocity of light down here. Here's the perceived mass from someone observing you, or you observing everyone else for that matter. And as it approaches the speed of light, the mass gets higher and higher to infinite levels, whereby you then need when you hit the speed of light, you need an infinite amount of energy to keep accelerating, pushing you along, which of course there is no infinite amount of energy, that doesn't exist. So you cannot reach the speed of light because of that. So that's the nice sort of intuitive way to look at it. And you can delve a little bit deeper and go to the concept of relativistic mass. And one of Einstein's, out of all that relativity, special relativity, derived from those formulas is that E equals mc squared, and he produced a whole paper on it, proving that energy and mass is the same thing, but just expressed as different entities, but it is the same. And as you approach the speed of light, mass and energy sort of become more and more similar in property, and it's called relativistic mass, or your resistance to acceleration. And it refers, they start just, instead of deciding it's mass, they start putting the kinetic energy of the movement into the equation to work out the relativistic mass. And you can see they've put it here. The energy of in the transformation equation, you get mc squared, so there's energy, they put mc squared in here. So your relativistic mass, which includes the kinetic energy, gets higher and higher and higher. As you approach the speed of c, the total energy approaches infinity, which an object cannot possess infinite amount of energy. So notice that rest mass is invariant. If, in other words, you're chugging along, you don't think you're getting more resistant, but people are observing you and you're observing everyone else relatively as well. So that is why you can't observe anything to go faster than the speed of light. It's because of relativity. So here's back, food for thought. And it also means you can have your hot cup of tea at 30,000 feet, travelling at 600 kilometres per second. Light doesn't get stretched out or doesn't get bunched up to higher or lower energy wavelengths. So you put it in the microwave, you get microwaves that heat up, because Einstein was quite right. There's nothing special about light. It just simply follows and obeys that original Galileo relativity principle that Newton said. The laws of physics are all the same for everyone at a uniform motion, and they just forgot to tack light onto that, which Einstein came along and did, thanks to Maxwell and the Michelson and Morley experiment. So there is nothing special about the speed of light. It just happens to be the same as the universal constant c, and it's the maximum speed at which a massless entity, such as light, has no mass, or information, causation, that travels across the empty space. Empty space has a natural resistance, and that just makes sense. Empty space is a busy, busy place. It's foaming with activity. So here's your 3 sticky messages you're going to take home. The speed of light is the same for all observers in uniform motion. Everyone, no matter whether a light source is coming towards you, away from you, or you're travelling away from it, everyone agrees the speed of light is the same. They detect it the same. Space and time are irreversibly entangled into one entity, space-time. You can't separate the two. And the implications include differing observer perceptions of space and time. Length contraction alters the perception of space, and at these high speeds, time dilatation process alters the perception of time. That's what's going on. So, Einstein's theory of special relativity tonight, Demystified. Thank you for your attention. I hope you've enjoyed it. Thank you. As for the equations, I regret nothing. Any question? It's like, I think all my 3 cats look like that some days. Any? Yes.
When you calculate the time dilation,
Yes.
your length dilation.
Yes, because your time, it gets complicated bringing the two together. The time is the person who appears to be stationary when they're looking at someone else, their clocks appear slower, as opposed to that person travelling length. So you've got to calculate them separately, but then you bring them together. Like that, the twin paradox, I brought them together there. And that's very easy to do. But you don't get messed up, treat the 2 equations separately, but be mindful in your mind who's seeing what. So Trevor on the Earth, he was looking at Roger. He was seeing Roger's clock go slower. Now, but Roger doesn't see the same because you've got the acceleration process, but in theory, Roger would see Trevor's clock going slow. And then there's the length contraction. That Roger, when he was travelling there, he looks out the window and it only looks like 2.2 lengths, but his clock was running normal, but he saw the length contraction. So you do treat them separately, but you bring them together. And for example, one of the questions in the exam actually was prove that in actual fact to both observers the clock was running exactly the same. If you had a telescope and Roger and Trevor could look at Roger's clock, and with Roger you could actually calculate and show that they all agree on the whole principle that things are unfolding, compensating for each other at the same rate. Yeah. But you treat the equations separately, but it comes out in the wash. Those times are fact. Yeah. Yes?
Yeah, if light waves don't get shorter or longer and the speed of light's always the same.
Yeah, and for a uniform, we're talking no acceleration here, for a uniform velocity.
So the redshift, is that because of acceleration?
Redshift, you got gravitational redshift, trying to accelerate out of a gravitational well. But also with your redshifting, that's the Doppler effect, and that's because of light is coming towards you. It's accelerating, that's a different scenario. Yeah, that's the Doppler effect.
The speed doesn't change, but the frequency does.
Yeah.
Because when you measure the frequency of light, you still measure the same speed, but if you were travelling towards the source, you would measure a higher frequency.
Yeah. So that's the Doppler effect, the wavelength, that's the best way, that's the Doppler effect, different again. And your redshift that you get with gravitational, because that's involving acceleration, trying to get out of a gravity. Once again, as Bill said, the reason you get gravitational redshifting is because the speed of light is not changing, but it's losing energy as it pulls away from a heavy body, so the wavelength gets weaker and weaker and longer. John, yeah.
Interesting thing. As late as I've got an old weekly news from 1930, about the time of the earthquake in Napier. That in the news there, we're still talking about ether. In 1930, they were still trying to decide, was there such an entity?
Yeah. So
instead of the diffusing
so John's saying, the ether that was kept a while. The Michelson-Morley experiment didn't just totally dismiss it. It did a lot of minds, but it took some years. John was saying in the 1930s, there were still people talking about the ether that's out there. So things didn't change quickly. And I think that also highlights Einstein's brilliance, how ahead of his time he was. 1905, he picked up on, because there they were, Lorentz and Fitzgerald, they still believed in the ether. They said, no, it's just that the speed of light is different. There's an ether out there, guys. We've got to find some other reason. And it was Einstein who came along and said, no, you guys have got it all wrong. So it was 1930s, there was still a lot of people talking about the ether. Yep. So it highlights how clever the guy Einstein was. Yeah.
Well, some members, I think, have been to the Large Hadron Collider tour. As Alistair, I think, did you go on it?
Yes. Ken and I were there in 2019.
Well, they're accelerating tiny subatomic particles, protons, but to do that, to power the magnets, to get those protons going so fast, they've actually got almost a dedicated power station to do it. And it's because of the mass effect Chris was talking about. As the particles are accelerated, it gets harder and harder to make them go any faster, more and more energy. But the curious thing is, I think, it's about 7 trillion electron volts as a measure of energy they put into those protons there, but some cosmic rays that come from outer space protons have got many orders of magnitude higher energy than that. So the question is, how does the universe do that?
It was about 2 or 3 years ago, the newspaper said, some experiment, they found particles travelling faster than the speed of C, light in a vacuum. And I think most people looked at it and they shook their heads and said, someone needs to recheck their data again, and sure enough, it was a data area. Now, another actually little anecdotal thing to bring up here, often people get confused about the speed of light and a vacuum. They say, Einstein said nothing can travel faster than the speed of light. Nothing can travel faster than the speed of light, that light travels in a vacuum. Light slows down in other medium. It travels slower in water and different chemicals and different medium and stuff. So there are other circumstances where something can travel faster than the speed of light in that particular medium. So there's nothing stopping something from travelling faster than light in a particular medium. It's just you can't travel faster than that, sort of rounding up, 3 times 10 to the 8 metres per second. You can't travel than that figure. Don't try and compare light in another medium with another particle in that same medium. It's not comparing apples with apples. And another people get a little bit confused if they say, how about these faraway galaxies that are receding from us faster than the speed of light? And they say, nothing can travel faster than the speed of light. I go, whoa, nothing can travel faster than the speed of light in a vacuum. That says within our universe. That's saying nothing about space-time. The reason those galaxies aren't travelling, faster than, zipping through space far away from us, the speed of light. Space-time is expanding. So the galaxies are sitting here just getting driven apart from each other faster than the speed of light. That's what's going on. So Einstein said nothing about the expansion of space-time, dark energy, which Jonathan spoke to about a couple of months ago. He just said, in our universe, in our vacuum, within our space-time, there's a natural resistance to the rate at which you can lay down electrical field and then some magnetic field lines and so on and so on. There's just natural resistance. Space-time can do its own thing quite happily, thank you very much. So that's I mentioned that little anecdotal little thing in there too that people often raise. So I think I hope you've all had some fun. Go home and turn the TV on and enjoy some special relativity. Drive home safely, guys. Thank you.